So today we're talking about atmospheric composition forecasting. Changes in the chemistry of the atmosphere are important. It's an important topic for the Arctic modelers for monitoring large-scale hazards such as wildfires and their climate implications, as well as for understanding chemical processes that are unique to the polar regions. This topic is of interest. It's of interest to me because it bridges the previous federal Arctic research plan with the new Arctic research plan, which has more of a focus on risk assessment and hazard management for Indigenous peoples, of which air quality assessment and prediction may be a component. So with that, we'll begin today's presentations with Emma Knowland. She is a research scientist, as we've heard, with NASA Goddard through the guest star program at Morgan State University, and she'll be giving an introduction to the GEOS-CF system. Emma, do you want to share your screen?
Thank you. All right. Thank you very much for the opportunity. Can you see my screen?
That's very good. Yep.
Perfect. Great. So I'm going to give a brief overview on our latest product from NASA GMAO, known as the GEOS Composition Forecast System. And our office develops and maintains the Earth system model called GEOS that is mainly designed to advance the use of satellite data products. The GEOS Composition Forecast System, or GEOS-CF, it provides global historical model estimates of atmospheric composition, as well as daily 5-day forecasts of the major air pollutants like ozone and PM2.5. And how we do this is we take our GEOS weather forecasting system, which is used to support NASA satellite missions and field campaigns. Some of you may be familiar with the above campaign, so the GEOS model was supporting that mission. And we couple that with the GEOS-Chem chemistry model, which is full tropospheric and stratospheric chemistry. And so the GEOS-CF is run once per day. It starts in the early afternoon, so pretty much right now I think it's getting kicked off. And then in order to have the best initial conditions for our 5-day forecast, we first run what we call a meteorological replay segment. And this is similar to if you have a data assimilation system, it would be like the analysis, but because chemistry is so computationally expensive to also have the data assimilation system running, it would just be, right now, it's just too much. So we take the information from a previously run data assimilation system, and we rerun the past 24 hours, but now we couple GEOS with GEOS-Chem. And we run this model at the high spatial resolution here for a global composition model at a 1/4 degree, or about 25 by 25 kilometers. And we use the full GEOS atmosphere from the surface all the way up through the mesosphere. And this way we have now both the chemistry and the meteorology on the same spatial and temporal resolutions. And because each replay segment starts the next day's replay segment, we can actually stitch these all together for one continuous time series available to the public since January 1st, 2018. And so forecasts are available on archive to the public since January 1st of 2019. And so GEOS-CF is available to the public in a few ways. The GMAO has a mobile-friendly website, so you can look at it on your computer or on your phone at this link here, fluid.nccs.nasa.gov. And you can get both maps and data links to the here. And what I'm showing here is we have 200 pre-populated what we call datagrams. So here I'm picking Anchorage. It's associated with the above campaign. And you can see here vertical curtain plots of the forecast of carbon monoxide. You can choose NO2, ozone, PM2.5, and SO2. It gives you the surface forecast as well as some of the key meteorological features, precip, wind, and temperature. But then we can also get maps of some of these primary pollutants at the surface as well as total column. If you're interested in downloading the data, you can access it here, either directly download the .NET-CDF files, or if you're comfortable with programming languages, you can also access it using the OpenDAP server. And we do have quite a few new developments. And so now we have what's called the CF map tool. It's actually CF_map, and it will show you a map of NO2, ozone, or PM2.5. And then you can actually zoom in to any grid box that you'd like to be able to get forecast, as well as the historical or replay data from the model. And so just in quick summary, because I want to really give time to the Pam and Matt with the science talks, we have available to the public composition forecasts that are available globally since January 1st of 2018. We're currently updating the system, so look forward to that probably later this year, but you can access information either from the CF or the CF_map if you're interested. Thank you.
Thanks very much, Emma. We can take a question or two. Emma, who else runs a global composition forecasting system?
Yeah, so ours is one of a few that run global forecasts. We have ECMWF, their CAMS product. They run a global air quality forecast system. The Finnish meteorological group, they have one as well. I think the Salam, and I think that one might actually be the highest horizontal resolution available to the public. Many others will have regional models. I think there's also coming out of the States, there's the WACM model, but that's much coarser at 100-kilometer grid box. But if people are interested in other options, I can definitely point you to a list of possible forecasts. I can drop that in the chat.
Thanks. Yangli, you have a question. You have your hand up.
Yeah, I have a question, Emma. Thanks for the introduction. So I have a question. So when we want to know the detailed setup about these simulations, like either like a good person that we should reach out to?
Yeah, you can definitely reach out to me. I'll add this link here on the bottom of my slides. It takes you to the GEOS-CF information website, which has links to our documentation. And then if you have any other further questions, you can definitely reach me at my email.
Sounds great. I'm especially interested in the composition part. I'd like to know like which kind of emissions are used for these simulations.
Sure.
Thank you.
I skipped over it. We're currently using the HTAP for anthropogenic emissions. We're going to be updating that to the SEDS database because HTAP is 2010 base year, and so SEDS will bring us up to at least 2019. We do have QFED, so we do get near real-time information of fires, which Matt will probably talk quite a bit more about. And then we also have a bunch of online parameterizations for things like dust, sea salt, and biogenics.
I see. Have you tried other fire emissions like QFED or GFAS or something like this?
Yeah, we've been using QFED. I think there have been some studies with GEOS-Chem testing some of the other emissions. I don't have anything offhand, but I know we have done some testing with some of the others, but we are sticking with QFED right now.
Sounds good. Thank you.
And Joey, do you have a quick question?
Yes, I have a question. So hi, Emma. So my understanding is that we have the forecast data since January 1st, 2018. And my question is that do we have like reanalysis data since then? Like, for example, if I make some modeling now, then I have a like PM 2.5 modeling result. Can I compare my result with your result? Like, I consider your result as a reanalysis data, as a true observation data. Is that possible?
To a certain extent, yes. So the one-day meteorological replays, they have near real-time information of QFED and some constraint on stratospheric ozone, but for the most part, there's no other data assimilation of constituents in the GEOS-CF. Right now, we are working towards that. So you can use the replay segment, which is available since January 1st, 2018, to compare to your model simulations. But just keeping in mind that some of that, because it's run in near real time, sometimes our boundary conditions are projected into the future. They're the best estimate we have, unlike if we did a reanalysis where we would have maybe some of that information would be more realistic for that day.
For
We are
example, can
working
you
toward,
turn to the next slide?
yep,
Where you have the map. Here you have the map of the surface CO. You also have surface PM 2.5
correct.
since January 1st, 2018, I guess.
Correct. And so that would be our best historical estimate of what the PM 2.5, CO, SO2, NO2. If you're looking for those, if you're looking primarily for PM 2.5, though, and you're looking for a reanalysis, I would point you to the MERA2 reanalysis, and I can talk to you about that offline.
Okay.
We're working towards a composition reanalysis, but that's still some time away.
Okay,
Okay,
let's
thank you.
move on. If you have additional questions, you can enter them into the chat. But for right now, our next speaker will be Matt Johnson from NASA Ames, and he'll be talking about wildfire emission transport using GEOS-CF.
Okay, let me get this in the presenter mode. Swap this. Okay. So we're seeing my full screen now.
We are now, yes. Yes.
Okay. Well, thank you for having me once again. My name is Matthew Johnson. I'm here today to discuss a application of GEOS-CF in more of the higher latitudes, the Arctic region. And this is a study that I published last year in Atmospheric Environment, long-range transport of Siberian biomass burning emissions to North America during FIREX-AQ. Okay, so I'm not going to go into detail about the FIREX-AQ field campaign. Basically, it was a NASA-NOAA joint venture, which they took a lot of observations and modeling to get data, a lot of aircraft observations, try to understand the impact of wildfires on tropospheric composition and air quality. But one of the interesting things that they saw during the campaign, and it was also forecasted by some of these forecast models, was a lot of this haze being moved into the Pacific Northwest during the campaign. Here I'm showing a MODIS image. I'm putting Seattle there for reference. You can see this haze coming on off the Pacific onto the coast, and it got us thinking, well, you know, one, where was this smoke coming from, and what was its potential impacts on the background tropospheric composition or air quality in North America during this campaign time period. So one of the things we noticed from the forecast models and also from the satellite data and a lot of the press coverage, which I'm showing some of here, is during the summer of 2019, when FIREX-AQ was happening, there was anomalously large wildfire activity happening in the region. Of course, the next couple of years, 2020 and so on, have been also very, very active. So, but 2019 was a very active year for wildfires in Siberia. And this is just some of the press coverage that this wildfire activity received. So what we wanted to do is combine GEOS-CF with ground-based and satellite remote sensing and also in situ data to characterize the transport of this wildfire smoke and then quantify some of its potential impacts in North America. So to the right, what I'm showing here is just some true color images from MODIS. The red dots you can kind of see there are fire detections, and when you didn't have a lot of clouds, you could see this very thick smoke covering, enveloping, you know, the whole region of central and eastern Siberia. To the left, what I'm showing is the QFED wildfire emissions predictions that Emma discussed briefly. What I'm showing here is the month on the top part of this left panel, showing the monthly average wildfire PM 2.5 emissions. I'm kind of highlighting the area of large activity. The red is an area of central Siberia, and then the blue is kind of highlighting an area of active wildfires in the northeastern portion of Siberia, getting into the northern latitudes of this region. And then the bottom part of this panel is showing the daily time series of the PM 2.5 emissions. What we noticed from QFED is that there is very large wildfire emissions and activity in late July and early August of 2019. So I want to discuss one of the main observation points that we're using from the study, and really sparked a lot of the interest from me to look into this, is the aerosol and ozone LiDAR known as AMOLite. So this LiDAR was located in northern Alberta. You can see from this left panel here, in northern Alberta during the FIREX-AQ campaign. And this was one of the main observational drivers of this study. And the reason for this being is what I'm showing here. So the top panels, what I'm showing is aerosol backscatter from ammonite. And the bottom portion of this is at the same time the coincident ozone observations being made from the same LiDAR. I'm showing two different time periods of the times where the LiDAR was observing a lot of this wildfire smoke. July 28th, August 4th on the left, and then August 5th through the 15th on the right. And what we noticed from these observations is that there was coincident and spatial and temporal coincidence of these large aerosol lamina and these ozone enhancements, which is indicative of wildfire smoke transport. And these were occurring in the middle to lower troposphere, where you usually had very clean atmosphere in this region of Alberta. So we noticed the observations there, so we'll understand. We'll get some more idea about where it's coming from. What I'm showing from the left is WACM model, which was mentioned by Emma in the last talk. And what I'm showing here in most of these figures are the fire CO. So the model predicts the CO just emitted from wildfires specifically. And from these models, what we notice is that over Siberia, the transport over northern Canada, you're getting up to 50 ppb and more of CO just from wildfires over northern Canada. And to the right, what I'm showing you some high split back trajectories. The starting point of this is the ammonite LiDAR, and I'm starting these at the vertical layers of these large ozone and aerosol lamina that were observed. And there is two different transport pathways that we noticed from the high split back trajectories and then using satellite data in the next couple of slides. Is that at the end of July, you had, when you go back in time, you have this 3 to 5 day transport pathway over the Pacific Ocean, and it's interacting with the boundary layer of central Siberia, where the wildfires are very active at the end of July. And then the right portion, what I'm showing is the in the middle of August, where it was more of a trans-Arctic transport pathway going back 3 to 5 days, interacting with the boundary layer of this northeastern portion of Siberia, which is then, that was the region where you had the most active wildfires occurring in the middle of August. So we got a general idea about maybe the general transport pathways of this smoke from Siberia. So then we wanted to look into it a little bit more using models. So we're using GEOS-CF for the study, as mentioned, and then tropomy. And these figures are showing column CO. And these very large enhancements are associated with the Siberian wildfires. So to the left, what I'm showing is a 5 day period between July 27th, 2019, and then July 31st. And to the right is showing August 5th through 15th. To the left, what you can see here, and from tropomy and the model, is there's very large CO enhancements over central Siberia being transported generally directly to the east across the Pacific Ocean. And then by the time, July 29th, in the satellite and in the model, you can see that this wildfire smoke is connecting all the way from Siberia directly over the ammonite location. And here I'm showing the aerosol backscatter from ammonite the same time period. So the timing of these aerosol lamina being measured by the LiDAR match up exactly with the timing that's suggested by tropomy and GEOS-CF. And a similar feature was seen in late August. And these maps, I should have mentioned, this magenta X is the general location of ammonite in northern Alberta. And a little bit more evidence to suggest that these enhancements seen by ammonite are from the Siberian wildfire smoke. Here I'm showing GEOS-CF AOD, or the aerosol optical depth. This is for the July 27th through 31st time period. And then the fraction of this AOD that is from black carbon and organic carbon in the model, which is a main emission source of these wildfire combustion processes. And once again, seeing the same timing of this plume come across the Pacific over northern Alberta in the ammonite location, which was observed by the LiDAR. So here what I'm showing is a comparison of GEOS-CF. These are time series curtain plots of ozone and aerosol from the LiDAR on the left and GEOS-CF on the right. In the time period between July 28th and August 4th, is showing that there was very good comparison and the locations and general magnitude of these aerosol and ozone enhancements over the ammonite location. And what we wanted to do is take these same types of plots, but we wanted to be able to have a more quantitative measure of the tropospheric composition and air quality impacts of these wildfire emissions in Canada. So what we did is we performed GEOS-CF sensitivity simulations. So what we did is comparing these sensitivity simulations, which we turned off wildfire emissions in Siberia, and they compared those outputs from the model to the baseline model, which included the emissions of wildfires from Siberia, and looked at the Delta O3 and PM2.5, more of a brute force sensitivity simulation here. Looking the differences between O3 and PM2.5 to get the idea and a general quantification of the tropospheric composition impact of the Siberian wildfire during this. So what I'm showing to the top here is the summer 2019 average enhancements of ozone and CO and PM2.5. And this is at the surface. And then once again, I'm showing the amylite location. So what we noticed from in situ data at the surface, the model as well, is that these surface impacts were actually much smaller than expected. And this is because these lamina weren't mixing down to the surface effectively and just being transported vertically over the surface location of amylite. There was some more impacts in the higher locations, higher altitudes, according to the model, but around amylite, the surface impacts were pretty small. Downwind, they could have been larger if they get effectively mixed to the surface. However, what I'm showing to the bottom left panel here is the Delta O3 and the Delta PM2.5 from sensitivity simulations in the middle to lower troposphere. And what we saw here is that we were getting 10 to 20 ppb of ozone enhancement between 8 kilometers and 2 kilometers, which were directly associated with 30 micrograms per meter cube aerosol lamina enhancements at the same time. So the tropospheric composition impact from these wildfires was much larger than the surface impacts in the region we were looking at during this study. So those were the main conclusions and what we did in this study. Here's some conclusions written down here. I'll leave those here. I can answer any questions now or after Pam's talk, whatever we decide to do. Thank you.
Thanks very much, Matt. Let's just take some questions right now. But I had a question. So yesterday there was an IARPIC talk given by Payesh Jain from Natural Resources Canada, who tried to link high latitude wildfires to blocking events. Do blocking events and the associated large scale substance explain or contradict the boundary layer interactions that you showed?
So I'm not exactly sure, but usually when you have these blocking events or high pressures, you kind of compress the PBL, and you might not be able to effectively mix down. But if you have a lot of surface heating, like you do, say in the LA or so Las Vegas per se, where you can get 3 kilometer deep PBLs, then you would be able to mix down more effectively. But the PBLs in this location, in northern Canada, are much smaller or much lower to the surface. Okay,
that makes sense to me. Are there any other questions? You can just unmute and ask. Oh, Mike McCracken has his hand up.
Do the models include cloud aerosol interactions? So if you put more aerosols in there, do you get cloud brightening or darkening or other impacts?
So certain models do. GEOS-CF does not have cloud aerosol interactions, but some models do have that.
I should point out that our seasonal forecasting system does have that. It hasn't been successful as yet in our NWP system, but they're working on that.
I just might say that, it would be really interesting to know if cloud brightening is occurring, and if that capability is there to actually go back to the 1980s and 90s or something and use emission inventories that had much more SO2 in the North Atlantic basin to know if cloud brightening was occurring, and if then the loss of cloud brightening might have led to accelerated sea ice melt or something like that. So there's
Yeah.
A lot of interesting questions. I mean, there is a modeling paper about that, but it would be really interesting to see that studied.
Matt, I believe the Wacom model does have that. Is that correct?
So I use Wacom outputs for forecasting. I don't know the nuts and bolts of the Wacom system.
Okay, but I think the latest round of the IPCC models have tried to put that in.
Yeah, and they could have different modes that they run the model, and their forecast may not have it, but their research reanalysis product, they might have that turned on.
Yeah, my understanding is most climate models include aerosol climate interactions for biomass burning aerosols. Yeah. So I have a question about, could you talk more about how the plume injection, do you have a built-in plume model, fire plume model for the initial injection of those biomass fire emissions?
GEOS-CF has a more, it's not like WRF-Chem that takes in more, it's not like a FRIDA's model that has information that you predict at injection height. Emma, correct me if I'm wrong, but this actually actually puts a certain percentage of the emissions above the PBL at certain locations and then transports it in that way. Emma, is that correct still?
Yeah, that's correct. And the exact numbers of how high that is and the percentage is escaping me, but I can look it up and drop it in the chat if for that answer.
Yeah, I'm just curious because for climate models, different models do that differently. Some inject a certain percentage to up to like 6 kilometers. I'm wondering if, for example, for some strong fire, they may inject higher. So I'm wondering if the injections depend on the fire intensity or burn area or something like that.
Yeah, I mean, there is pyrocumulus events happening all over during the summer of 2019. You can just look at the satellite images and see, so there was times where there was, higher injections and lower injections. So it was very hot temperatures for sure at the surface.
Yeah. All right. Thank you.
Thanks. Any other questions? If not, and hopefully we'll have time for a discussion at the end, we can go on to our next speaker, who is Pam Wales from NASA GMAO. And she will be talking about a topic that is a favorite of mine, bromine explosions. Pam?
All right. Let me make sure you guys all seeing the right screen.
Yes.
Good. All right. So I'm Pam Wales at GMAO, and I'm looking at detecting bromine explosion events using satellite observations and GEOS-Chem. And I'm running GEOS-Chem coupled to our GEOS system in a setup that's similar, but not the same as what's done for the CF system that Matt and Emma have talked about. All right, so in this figure, I have column measurements of bromine monoxide collected by the ozone monitoring instrument, where you have this really large amplification in bromine monoxide over northern Canada. And these bromine explosion events, as they're termed, are associated with near complete removal of surface ozone. So what we want to do is use GEOS-Chem to try to separate how much of this column is actually due to surface emissions of bromine, and then evaluate its impact on surface ozone. So as I mentioned, there's near complete removal of surface ozone. On the right, I have in black observations collected at Ukqiavik along the northern coast of Alaska. And this is over a 4-year period. And during polar spring, there are these events that are where ozone is near zero. In blue is GEOS-Chem, and I'm using a version of GEOS-Chem, the GEOS-Chem mechanism that doesn't include polar emissions of bromine, and it's really just not capturing these low ozone events. And then these low ozone events are related to very different changes in the oxidative capacity of the region, and it increases the biouptake of mercury. So currently the exact mechanism for how bromide from sea salt is converted to reactive bromine that's transported in the atmosphere. There isn't a good consensus between different global models for how to model this. So what we want to do is use GEOS-Chem, and we're running this with a coupled stratospheric and tropospheric mechanism, because satellite observations are measuring the total column of BRO, so from the top of the atmosphere down to the surface. And we need to remove, there's a significant stratospheric component to this that we need to remove to actually get at the troposphere. And this is being run coupled to mirror to meteorology in our GEOS system. So we found that overall column BRO in GEOS-Chem is biased low with respect to OMI. And then in black, I have the mean column BRO as a function of latitude from OMI. The gray is the standard deviation. And then from GEOS-Chem, the majority of the column is in the stratosphere. And this is in relatively good agreement with some stratospheric column measurements from ground-based instruments. But the troposphere is fairly low. And with the version of GEOS-Chem that we're using, we know that there are going to be updates to the tropospheric mechanism moving forward. We don't have sea salt aerosols in this, and so that's going to increase the tropospheric component. So what we want to do is really just define a statistical bias threshold to say where our OMI measurements large enough that really we can't justify it based on the background BRO. It's actually these polar events. And so I look at the difference between OMI and GEOS-Chem outside of polar regions, so between 50 south and 50 north, to try to get rid of regions that might be affected by polar emissions. And we have this really nice normalized distribution centered around 1 × 10⁻13 molecules per centimeter squared. And we define a bias threshold that's greater than 99% of the bias that we observed at lower latitudes. This is 3 times standard deviation plus the mean bias. And so this is going to be a lower limit estimate for what we think is being emitted from Arctic bromine. And then we do have a sensitivity study where we look at a slightly lower bias threshold. So going back to a couple days where OMI detects high amounts of BRO over the Arctic. The top row here is OMI BRO, and the bottom is the column in GEOS-Chem. And so below that, where I have the arrow pointing to it, is the tropospheric hotspots. And so we're only highlighting pixels where the difference between OMI and GEOS-Chem is larger than our bias threshold. So if there are polar emissions that are don't result in an amplification to the column, we're going to miss that from looking at the satellite instrument. So to calculate bromine emissions, which we're implementing the model as molecular bromine, or BR2, that's going to then photolize and feed into the BRO cycle. So we're only observing BRO, but really that's a part of a family of bromine compounds. So we have to make some estimates for what fraction of bromine is observable as BRO, and then how long that's going to remain in the system. And the resulting, once we implement that flux in the model, you get the columns along the bottom row. So in general, we are able to capture the magnitude of the tropospheric the OMI-based tropospheric hotspots, and we're generally well correlated with it over the course of the day. But there are some regions where we do either over or under represent the tropospheric hotspot column. And so these are some monthly mean statistics where I'm looking at the column of BRO from the tropospheric hotspot, and then the increase in GEOS-Chem upon implementing the flux. And we do have a slight, this is for 2012, and we do have a slight high bias in April, late April and early May. But overall, we are generally capturing the tropospheric hotspots for this time. On the right, I have some surface ozone statistics, and this is how much has surface ozone changed in GEOS-Chem relative to our standard simulations. And so we're detecting how frequently do we have significant decreases in ozone. So this is where the change in surface ozone is either greater than 25 or 50%. And we do have like isolated but significant decreases in surface ozone more later in the season. You can see we're not capturing much that's going on in March. But later in the season, it gets to be a little bit more widespread, but if infrequent. And so I have some locations of some surface ozone stations indicated as red triangles. If I move on to my last slide, this is observations of surface ozone collected at 3 coastal stations. In black is the observations, in blue is GEOS-Chem without polar bromine emissions, and the red is after we implement our lower limit flux. And so we are generally underestimating the loss of surface ozone that was measured by these stations. Our simulations are going to be very sensitive to both the background amounts of VRO as well as the bias threshold that we're using. So it's a catalytic destruction of ozone, so that it involves a self-reaction between 2 bromine monoxide molecules. So we're going to get a nonlinear response as we increase bromine. So what we've done is tested if we just drop our bias threshold to 2 times the standard deviation. So it's really not that much of a difference in terms of the magnitude of the bias threshold, but what it results in is that bromine is detected over a larger surface area, and we end up emitting about twice as much bromine. And we do start to capture in yellow, if you can see that, we start to capture more of the surface ozone decreases later in the season, but we're still missing surface ozone decreases in March. And so GEOS-Chem is a really active user community. So we're hoping that by keeping our estimates as a lower limit estimate, that we can, our flux calculations will be play better with the mechanism as it evolves, because there are efforts to improve the sea salt aerosol representations and improve the heterogeneous and washout of bromine compounds. That's all I have for today. Thank you.
Thanks, Pam. So again, a review: of bromine explosion is the sudden, apparently catalytic elimination of ozone near the surface, which leaves a strong bromine signature. And these have been observed since the 1980s, I think I was reading last night, and they've also been observed in the Southern Hemisphere as well.
Yes, and I do ignore the Southern Hemisphere for now. I find that the biases between GEOS-Chem and OMI are persistent throughout a lot of the season, and I think that could be because sea salt aerosol is going to be more prevalent in those regions along the Southern Ocean. And so I can't really definitively isolate the Arctic emissions there.
So my understanding of GEOS-CF, and you said that GEOS-Chem is an active community, that new parameterizations can be developed and submitted for review. And my understanding is that there is a blowing snow parameterization that has been submitted. There is no blowing snow representation in the GEOS-NWP model, but I guess there's a parameterization for GEOS-CF. So there had been some discussion about whether blowing snow events were related to these bromine explosions. Can you elaborate on that a little bit?
Yeah, so I think it's version 13.2. They added blowing snow, sea salt aerosol, and the bromine release from that. We don't have that in CF, and we're updating to a version of the GEOS-Chem mechanism that's going to be before that addition. I think what I'm putting in here, what I'm estimating is going to be much lower amounts of bromine than what's in that. Part of that could be I'm just missing some of that from the satellite instrument, but I think having both methods for looking at Arctic bromine emissions could be useful for research studies.
So apart from the fact that these events are shocking, it's a complete elimination of tropospheric ozone when these things go off. Has anyone tried to connect a type of climate impact or anything like that to these events?
Yeah, so I know of one study that looked at satellite observations of bromine monoxide over a fairly long period of time, going from like GOEM to the GOEM-2 instruments. And they saw an increase in bromine explosion events. And I think they connected it to increases in first year sea ice relative to multi-year sea ice. So the first year sea ice is going to be more enriched in sea salt than the multi-year sea ice. Yeah.
Okay. Are there any other questions for Pam?
Hello. Can you hear me?
Yes, go ahead.
Yeah, my name is Kenjiro Toyota from Environment Canada, and we are working on this type of chemistry using our model. And yeah, we are actually concerned about the more on the snowpack itself, rather than the something, you know, blown up in the sky as a blowing snow or the sea salt aerosols produced from it. Are you going to take care of that aspect of the snowpack chemistry as well?
So I don't have a treatment of snowpack chemistry. I kind of tried to get around that by just emitting BR2 wherever our OMI detects BRO. I do know that, so the blowing snow mechanism has been added to GEOS-Chem, and then there's another study on top of that that is trying to look at blowing snow plus snowpack releases. I'm curious how that's received by the wider community, because these are really large amounts of bromine that are very reactive. And I think if like users aren't like specifically looking at these events and like know to look for them, they could be a little bit wary of what it's doing to ozone. But yeah, that is a very important, the recycling of the bromine on the snowpack is very important for these studies.
Okay. And regarding the current sort of discrepancy you found between your approach and the observation in terms of the ozone depletion, you seems to be missing a lot of bromine release in early spring. And is it related to the way you screen out the data for the satellite, like solar zenith angle and things like that might be affecting this discrepancy?
Yeah, so I think it could be a combination of things. So I can't use, like in March, there's a lot of OMI data that I can't use because the solar zenith angle is too low, like you said. So if there's emissions over beyond, like I think 70 north, I will miss that. There's also the stratosphere is going to be more active in this period of time. From what I can tell, the stratosphere is doing okay in GEOS-Chem, but it's gonna be much noisier and harder to pull out the troposphere then.
I see. Okay. Okay. Thank you very much.
Thank you.
Thanks. So Pam, you touched on OMI. Is OMI used in GEOS-Chem? Are the OMI observations inserted into GEOS-Chem or?
So OMI is used in our FP ozone assimilation.
Oh, it is. That's right.
Yeah, so in what I'm doing with GEOS-Chem, I'm not nudging ozone. Ozone is just completely calculated free running. But in the CF system, that's going to be nudged to in the stratosphere, it's going to be nudged to ozone observations that have seen OMI.
So the question I was going to ask you and the other speakers as well is, what types of Arctic observations do you think would be useful for improving your simulations and forecasts? I guess more observations of bromine explosions would be good.
Yeah, I always glad to see more observations of bromine.
But you've relied on some surface observations here as well, right? Of ozone profiles. Are there a lot of those in the Arctic?
So you have some pretty long records at Eureka and Alert. I think all the, yeah, also at Ukivik, you have some records. Emma might speak better to that than I can. But I mean, I'm not opposed to more observations, particularly if ones that go into the lower stratosphere, now that we're looking at more ozone hole events up there.
Yeah,
so
it would definitely be, we would always say all and more observations anywhere and everywhere. But I know that's really like ambiguous, but it is tough to get continuous observations as well. Like I think it's one of the things that we struggle is getting ones that have the long time series and that get some type of vertical information is always helpful.
So, but these are just NWP forecasts, and your record doesn't go back that far. So what is the necessity of these longer records?
Well, we are going to be running do a composition reanalysis alongside our next meteorological reanalysis, which will cover the period since 2000. So we are right now our GEOS-CF is mostly focused on these recent, 4-year period, but we will be going further back.
Okay, and I was going to ask Matt Johnson what observations would also be used for wildfires, but before that, Mike McCracken, do you have a question you want to ask right now?
Just a quick one. I guess I'm wondered if everybody is prepared in case there are volcanic eruptions to try and put volcanoes in there and see what happens. If it occurs in Alaska, which seems to happen often.
Well, I think there are a lot of aerosol observations that go in. We certainly looked at that in the GEOS system for the Tonga eruption. Emma, do you want to say anything else about volcanic eruptions?
Yeah, it's hard in the near real time to know how much to put in and how high all that information. It's very difficult, but when running a reanalysis, if we can go back in time and we have some of that information where we can actually say how long it was erupting for, what the injection height is, then we can handle that much better. But in near real time, we generally don't have that set up in the system.
It's actually interesting. For my paper, I was actually looking at the potential stratospheric impacts along with the tropospheric impact of the wildfires, but that I'm going to butcher the name of this. The Russian volcano that erupted in 2019, Radiki? Does anybody know the name of that?
I think it's
Okay.
FIREX-AQ.
Yeah, so that was erupting, I think it erupted like a month maybe before. And when I started looking into it, that the aerosols from the volcano and the Siberian emissions, you couldn't really discriminate between them in the stratosphere. So I had to remove that whole part of the paper.
Now, what other types of observations do you think are useful for looking at emissions transports?
It's always the cheap answer from modelers, more observations, but maybe, and Melloway, who is online, will talk to us more. More observations either from remote sensing or in situ about aerosol speciation is always nice. PM 2.5 and total aerosol is great from satellites, but if you can get some more speciation from that in vertical resolution, like if you had a airborne satellite HSRL, but it covered the whole globe all the time, that would be the most amazing thing for wildfire transport.
Okay, it's the top of the hour. And I think we'll end here. I'd like to thank very much our speakers for today. I thought this was an excellent discussion. And hopefully it's a starting point for looking at composition modeling in the Arctic in more detail over time. So I'd like to thank everyone for participating as well. This has been a really great meeting. And Hazel, do we have anything else to add?
I think that's it. Thank you so much to our speakers, and thanks everyone for a really robust discussion. This was excellent.
Thanks for having us.
I think next month's modeling meeting is a listening session
For the new plan.
With a new plan, that's right.
And I think that's March 16th, if I'm remembering correctly, but just keep an eye on the website and we'll send around an email in the next few weeks. So thanks everyone.
Okay, thanks very much.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.